Good morning, everyone. My name is Sinu Ravi. I'm working as a research professor at the Department of Chemical Engineering, Yonsei University, under the supervision of Professor Yun-Sung Wei. Here we go. My presentation title is Hydroxyl-rich organic nanofiber polymer for superfast capture of pharmaceutical contaminant from water. This presentation contains as the introduction to PPCP and the polymer material synthesis, characterization, and which follows the result and discussion, and finally the conclusion. Introduction to PPCPs. PPCPs are nothing but pharmaceutical and personal care products, which also called as micropollutant. The emerging micropollutant contaminant in recent times receives immense attention because of its toxicity, even at the extremely low level in the water medium. And thus, removal of PPCP receives great attention. In general, there are different kind of PPCP exist. However, they fall into three subcategories, which are antipyretic, anti-inflammatory, and antipyretic materials. These PPCPs are removed in this work through absorption process because absorption is very simple and economical compared to the other process which is frequently used for the water treatment, such as ultraviolet irradiation and ion exchange methods. So for this, here we have synthesized a porous organic polymer. In general, porous organic polymers are formed via covalent bonding network. This covalent bonding follows the principles of reticular chemistry. So porous organic polymers, in general, they have high surface area, large pore volume, and tunable pore structures. When the porous organic polymer have high functional group, and we can expect that which can give high absorption behavior towards any PPCP materials. So for this, we have used two monomers. One is the mesohydroxybenzone, that is MHB. The other one is the tetraphenyl 1,2-ethane diol. This is another monomer. Using these two monomers, we have prepared three different polymers. So when we treat this mesohydroxybenzone under the brittle graft condition, which yields the HPOP1 as the final polymer. So meantime, when we treat this 1,2-tetraphenyl diol under the brittle graft condition, which gives HPOP2 as a final polymer material. Interestingly, when we treat these two monomers, such as this mesohydroxybenzone and 1,2-tetraphenyl diol under the brittle graft condition, which gives HPOP3 as a final polymer material, which also called as PONF. I will tell you why this will be also called as PONF in the later slides. So further, this porous organic polymer were characterized using different characterization technique in order to confirm the successful synthesis. So initially, we have used the FTIR analysis. The characteristic peak for the C single bond C and the C double bond C stretching frequency were observed both in the precursor as well as in the polymer material. So meantime, the characteristic peak for the CH stretching frequency and the OH stretching frequency at nearly 3000 and 3500 were observed both in the polymer as well as in the monomer material, so which confirms the polymer is successfully synthesized. In addition, there is a characteristic peak for the HPOP1 at the range of 761. So as you can see here, the same peak is also obtained at HPOP3 material. However, the peak intensity at HPOP3 is only 50% when compared to the HPOP1. Meantime, there is no peak at 761 in the HPOP2 material. So which suggests that HPOP3 is formed by the two monomers. One is this mesohydroxybenzone, The other one is tetraphenyl ethanediol. Further, the crystallinity of porous organic polymer is analyzed using the XRD, X-ray diffraction technique. As we can see here, all these three materials shows broad peak at 2 theta range of 22 degree. So which suggests that all these three materials are amorphous in nature. Further, the porosity of materials were analyzed using the N2 absorption-desorption isotherm. All these three materials shows nearly type 1 kind of isotherm. For HPOP1, the absorption at the initial P by P naught value is not so high, so which suggests that the microporosity fraction in the HPOP1 is comparatively less when compared to the HPOP2 and 3 because they have the high absorption at this low P by P naught value. Meantime, all these three materials gave the moderate absorption at the P by P naught value from 0.02 to 1.0. And further, the pore size distribution is calculated using the NLDFT method. As we can see here, the pore size for the HPOP1 from 1.32 to 5.36, and for the HPOP2 and HPOP3, and the pore size ranges from 0.7 to 2.88. The surface area of these materials are in the order starting from the HPOP1 to 3 is 91 meters square per gram, 477 and 552 meters square per gram. Meantime, the pore volume also follows the same order as with the surface area, as we can see here. Further, the presence of chemical element in the polymer were analyzed using the XDS analysis. So as we can see here, the characteristic binding energy peak at 283.5 is ascribed to the C single bond C and C double bond C linkages in the polymer. In addition, the peak at 284.5 is characteristic to the C single bond O linkages, and the peak at 288.1 is characteristic to pi star interact transition. So we can also see that the peak at 531.1 is characteristic to the oxygen linkages with the hydrogen as well as carbon. So this peak area of this oxygen is in agreement with the theoretical value we have calculated. Further, the surface morphology of the material were analyzed using scanning electron microscope. As we can see here, the HPOP1 material has a foam-like structure with a particle size of nearly 10 micrometer, whereas the HPOP2 has the spherical type nature with a particle size of nearly 1 to 2 micrometer, whereas the HPOP3 has the unique morphology, that is a fiber-like structure with a particle size of maybe 10 to 15 micrometer and the particle width of around 50 nanometer. These are the illustration image drawn using the 3D software. So here and further, the porosity of the material were also analyzed using the chem analysis. These 2D images were shown that all these three materials having the large order and have the hierarchical porosity. And as we can see here, the H2O3 has having the high fiber nature, and thus it is also called as a PONF. It's nothing but porous organic nanofiber. And further, the mechanism for this polymer formation is derived. So, in order to synthesize the HPOP1, the mesohydroxybenzoin, that is MHB, is treated under the Friedel-Crafts condition. So this monomer having the linear structure and it has two reactive ends, as it is marked here, two reactive ends. The interaction between this end in the polymer synthesis is yielding this foam-like particle. Whereas in the HPOP2 synthesis, the monomer is TPED, that is tetraphenyl ethanediol, and it has a four reactive end. The interaction between these ends successfully yielding the interconnected 3D structure of the material, and it's giving this spherical kind of particles. And when we do the reaction using these two monomers, and it gives the H2O3 as a final material, and it has two steps. The first step is the linkage between these two monomers and giving this unit, and the second step is the linear growth of this big unit and resulting the H2O3 or PONF as a final material. Further, these three materials were used for the absorption of PPCBs. In the absorption studies, we have obtained PONF for high absorption capacity compared to the HPOP1 and HPOP2. So that I have shown only for the PONF here. So in the absorption study, with increasing pH, the absorption of DFS, SMX and AMP, they are nothing but diclofenac, sulfamethoxazole and acetaminophen. With the increasing pH, the absorption is also increased and reaches the optimum value for the DFS at pH 4. And for the SMX, the optimum pH value is 4.5, and as also for the AMP, the optimum pH is 4.5. And further increment in the pH resulting in the decrement in the absorption percentage. The reason for the low absorption at lower pH is because of the protonation of adsorbent surface, which restricts the interaction of PPCP with the adsorbent surface. Meantime, the low absorption percentage at higher pH is because of the high concentration of hydroxyl ion, because of the NaOH being introduced in order to increase the pH, and those hydroxyl ion resist the interaction of PPCP with the polymer surface. And further, the kinetic behavior of the PONF towards this PPCP was examined. As we can see here, the PONF shows really fast absorption kinetics within 10 to 15 minutes of contact time. All the PPCP reach the equilibrium within 15 minutes of contact time, and the absorption capacity is also in this range. For the DFS is nearly 380 using the Langmuir model, and for the SMX is 330, and for the AMP is 252. And further, the absorption capacity which obtained from the Langmuir model is compared with the previously reported benchmark material. As we can see here, this material shows high absorption capacity compared to many material which is previously reported. Further, the polymer reusability was tested. The polymer can be used for at least 10 cycles. So, as we can see here, after the 10 cycle, only a small drop in absorption percentage is obtained, and this drop is not very significant, and it shows that the polymer can be used for the long run in order to remove the PPCP from the water medium. And the absorption capacity of the material is correlated with the chemical and structural characteristics of the PPCP material. As I have already told, that absorption capacity is in the order, like DFS has a high absorption capacity compared to the SMX and AMP. So here we can see the molecular weight of this material is also in the Meantime, the hydrophobic nature of this CPCT is also in the same order, which follows with the absorption capacity of that material. And further, the absorption mechanism is proposed by using SMX as a model compound. This absorption mechanism derived based on the pH study and the XPS analysis. In the pH study, the absorption was maximum at 4 and 4.5 for this 3 ppCGs, and which suggests that the absorption mechanism involves through the hydrogen bonding interaction. Meantime, there was a moderate absorption at lower pH as well as the higher pH range, which suggests that the absorption is also involved by the other factors, such as the pi-pi interaction and the hydrophobic interactions. And this figure shows the elemental peak from the SMX, that is after the absorption. As we can see here, before absorption there is no sulfur peak, but after absorption we can see the nitrogen and as well as the sulfur. And further, the chemical stability of material were analyzed by treating the polymer material into different pH medium for 72 hours. As we can see in the FDR figure, there is no change in the peaks or the stretching peaks of the chemical bond, and it suggests that the material is highly stable for that under the treated conditions. Meantime, the same material are also tested for the N2 absorption desorption isotherm. As you can see here, there is not much change in the N2 absorption desorption isotherm, which suggests that the polymer materials are highly stable. And further, in the recyclability process, the PONF is also tested with the fresh and the reused one using the FTIR and as well as the nitrogen absorption isotherm. As we can see here, there is no change in the FTIR peak. This suggests the material is stable so that we can use the material for the long time. Meantime, there is very small decrease in the surface area, and that decrement is not very much significant, and thus it also confirms that the material can be used for the long time. So in a conclusion, we can say that we have preferred porous organic nanomaterial with high surface area, and the material exhibit high absorption capacity towards different ppCT with enhanced kinetic behavior. So we would like to thank the NRF from the Korean government, and this work we have published this work in the Environmental Science